class, we are now on 2.1b. This is units of measurements. Now, science does not exist at all without measurements and units. This is how all the science that we know, how we research, everything that we do has values and measurements and units to it. So units of measurement are quantities or values with accepted values. And these values and units are understood and accepted in the science community. So when you speak about a measurement has a value, a number, and a unit that goes with it anytime a measurement is taken. And that unit always corresponds with that value. And if nothing I'm saying right now makes sense, it will as we start getting into the math of it. Why are units of measurement important? And why do we need to keep this streamlined across the science community? This is a perfect example why. In 1999, 125 million Mars climate orbiter was lost due to unit confusion. Why? Because Lockheed Martin's software program used imperial units, which is U.S. measurements, what we normally would use, while NASA used SI units, which is the metric system, and they are not equivalent. So while one program was using English measurements, the other one was not, and they believed that it crashed somewhere once it got into orbit. It just crashed because if I understand this right, what would have allowed it to continue its way onto Mars, the distance wasn't long enough based on the units. There wasn't enough, the conversion didn't match, so it crashed instead, is what they believe happened. If you look on Wikipedia, this is actually interesting because some people did catch this and then they were ignored pretty much. So I'm not sure what this whole thing was, but it was a big deal. And this is a perfect example of a science community not working together on something very expensive. So we're going to start getting into metric units, and this is something that we don't tend to use in the United States, even though we actually do use some of it. If you look on like bottles of liquids, sometimes you will see things in liters and milliliters in parentheses on there. So it's not used as much as, obviously other places, but there is some writing and it does exist around if you pay attention. So common English units, we tend to use a foot and a mile for length, but in metric units, it's a meter. And 1 meter is equal to 3.285 feet. So a little bit more than 3 feet. And 1 kilometer is 0.621 miles, so more than half a mile. Mass or weight, metric is kilogram, and we tend to use pounds. And 1 kilogram is equal to a little over 2 pounds. And volume, metric system uses liters, and we use gallons. So you think of milk, a gallon of milk, and so forth. So 1 liter is 0.264 gallon. So we're going to start moving over into the metric system and say goodbye to the English system as you start progressing into chemistry. So one thing I want to point out that your book does not talk about, it says here mass or weight. I want to explain the difference between mass and weight, because eventually the term weight is going to go away and you're going to use mass all the time. And if you do use weight, it's kind of loosely used, but you understand the difference between mass and weight. We use mass instead of weight. Why do we use mass? Mass is a measure of the amount of material in the object. Sounds like weight, right? It's based on the kilogram as the base unit. And that part really doesn't matter. What you need to know is that an object has one weight on Earth and another on the moon. However, the mass does not change, and that's the difference between weight and mass. Why? Because weight is, for an object, is the force acted upon that the object due to gravity. So it's the gravity pull that determines your weight. However, the mass of an object is the same amount of it's the matter. Let me just read this. Mass of any object is the amount of matter that an object possesses, and that doesn't change. So think about the thickness of something. That's still not going to change regardless if you're on the moon or on Earth. Your weight does, because the moon doesn't have the gravity pull that Earth does. So here's an example of somebody that would weigh, 110 pounds on Earth, weighs 18 pounds on the moon. However, the mass is 50 kilograms, regardless if you're on the moon or on Earth. So this slide is something that you guys don't have. I just want to specify and point out why the word mass is going to be used now more than weight, even though your book doesn't seem to pick up on that yet, but it will. It'll eventually change and it'll be strictly mass. Okay, so fundamental units, these are the main units that we use for the metric system. Mass is kilograms. However, we tend to, kilograms is a very large unit, so we tend to use grams and smaller, in fact. Length is meters, time is seconds, and one thing I want to point out here is the units, the abbreviations. This is kg, this is m. Seconds is not SEC, that would be wrong and would be marked wrong, is parentheses is S. And we're going to do examples, and so this is not going to be a shock to your system on, when we start doing problems. Temperature is Kelvin, however, we also use Celsius, but when we deal with gases, we use Kelvin. You really don't need to worry about these, except for mole. Mole is something that we do use, and you will learn about it shortly, and some people struggle understanding the mole. It is something like a dozen. If you say a dozen, you immediately know that's 12. In chemists, we use the word mole. It doesn't equal 12, it equals something bigger than that, but it has a set number. And so when you say a mole, you will instantly start knowing what that number is equivalent to, which I'm not going to say now because it will confuse you. Derived units. These are units that are taken from these, and we use them still. So volume is meters cubed, and you can see meters as length. Why is volume meters cubed? Because volume is actually, it's length times width times height. So it's 3 dimensions. So if it's length, let me see if I can do this. Length, width, height. Length, width, height. There we go. And then velocity is meters per second. And density is kilograms over meters cubed. We tend to use grams over centimeters cubed. And this is density, which we will also cover, is mass over volume. So mass is volumes here and mass is here. So this is mass over volume, which you will also learn about. Okay, so when we use the metric system uses prefixes to describe something bigger or smaller. Where we would, and it's kind of hard in the English system, we don't have something similar to this, where we use one main unit and then we use a bigger prefix to describe something big, or we use a smaller prefix to describe something small. And metric systems do. And this is kind of hard for students to learn in the beginning. However, this is something that's never going to leave you. If you plan on taking all the chemistry that Chaffee has to offer, then you will never get away from this. So you will constantly be using this. I want to point out why, how the metric prefixes work. So your book talked about a wireless network that transmits data at 160 million bits per second. So that would be this very large number. Again, this would be something very difficult to write over and over again. Yes, you could use scientific notation, but you can also use a metric prefix. And it just makes the number written smaller. It still is equivalent to these are equivalent to the same thing. You're just writing it out to not have such a large number, but the prefix indicates that it's this exactly. So instead of writing it as this huge number, you can write it with the metric prefix and write it as 160 megabits. So bits is the base unit. And mega is the prefix. So where's mega? Mega is right here. It's large, so anything below this is less than 1. Anything above it is more than 1. And kilo is here. Kilo is 1,000. Mega is 1,000,000. So if we see this, you can see this is 160 million. That's what this means. When you say 160 megabits, that's exactly what you're saying here. So you are definitely going to need to know these prefixes. Yes, we are at home. If you were in person, you would definitely need to memorize these because they would be on the test in person. So I strongly suggest, to save time and headaches, you start getting comfortable with the names, how to spell them, and what they represent, and the symbols. Because the less that you have to refer to something that's written down and you just know it, you believe me, you save so much time. And if we had something like this, so what we see here is we have 1, 2, 3, 4, 5, 6 zeros in front of 32 grams. So this is extremely small. Instead of rewriting this over, we could write in scientific notation, or we could use a metric prefix. And we tend to use metric prefix. So let's see what this is. If we write in scientific notation, we can see that this says 10 to the negative 6 power. Well, we can go down here and we have a 10 to the negative 6 power. This means all these zeros. So we can write it as 3.2 micrograms. And if you understand what micrograms mean, and you know that it is equal to this, then you know that this is exactly what you're dealing with. And this is where we start getting into the math of chemistry, which some students have a hard time with in the beginning because it's something you guys have never dealt with, or at least some of you. I added this. This is not in your book because a lot of the books skip over the base unit, and I think that confuses students. It just starts at this one and then it goes to this one, but it never shows the base unit. The base unit is exactly what you're dealing with. So in this case, this is meters. It doesn't have to be meters. Could be liters. Could be other. We have other. I just covered some of the things in the previous slides. The meters tends to be the easiest one to learn. Now anything below this is less than 1. Anything above it is more than 1. And that's what it's. So instead of using like all these zeros, either going this way or this way, we can use the metric in front of it, and we can understand that it means either a large number or a small number. But it starts with the base unit, and you can see as the tens, as we increase in tens, it goes up, and as we decrease in tens, it goes down. So that's what these mean. There's deci, centi, milli, micro, nani, pico, femta, and atto, deca, hecto, kilo, mega, giga, and tera. Okay, so let's make sure you guys can understand what prefixes mean. It's a special feature of the SI or metric system, and a prefix is placed in front of any unit to increase or decrease its size by some factor of 10. It's a numerical value. So here, this is where milligram comes in and micrograms come in. I'm sure you guys have heard those. You just don't understand maybe what they actually stood for at the time. This is exactly it. If we look here, here's milligram. It is remember I was telling you about the placement of zeros? This is where this comes in helpful. This is tens, this is hundreds, this is thousands. So this is 1 over 1,000, or in decimal form. If you enter this into your calculator, this is what your calculator is going to give you. This is what it represents. So this is milli, and micro is 10 to the negative 6, and it's 1 over 1,000,000, and then you can see this is what it stands for here. So that's what these mean. Milligram, mg, microgram. You can disregard this. I should have removed this. It's just this, and if you don't know what this symbol is, what they use is a U and a G, and that also represents microgram. So again, you can start with a base unit. The base is whatever it is that you have, and you can make it smaller or you can make it larger. So if we want to make this larger, we add a kilo in front, and now we have 1,000 meters compared to 1 meter. So 1 kilometer equals 1,000 meters. 1 gram, that should be not an S, is 1 G. We want larger, is 1 kilogram. We now have 1,000 grams. And that's where you see here, kilo means 1,000 equals 1,000 milliliters, meters. Okay, so this is a slide from your book. How many meters are in a kilometer? I just covered that. 1 kilometer, if you see here, equals 1,000. 1,000 meters. How many amps are in mega amps? So if we look at mega is 10 to the 6, that's 1 million. So it means that we have 1 million amps. How many milligrams are in a gram? So I wanted to show you where this came from, because see, it shows you this, and then it gives the answer like this. How did they do that? Because if you look here, it says milli, has an M, 10 to the negative 3, and it's 1 over 1,000. Well, if you do the math, and this math is right here, if you multiply 1,000 on both sides, this crosses this out, leaving 1 gram. That's what you see here. And the 1,000 times 1 equals 1,000 milligrams. Or it is also in the form of 0.001. It's less than 1 though, so that's where you should know. It could be 1,000 milligrams equals 1 gram, or you can write it like this, depending on what is needed for it. And we'll go over exercises with that. So here are some problems from another of my books, my lectures. 1,000 meters is equal to, so what's 1,000? 1,000 is equal to kilo. So if we look at this, prefix is for kilo is 1,000, so it's 1,000 meters equals 1 kilometer. Now let's look into smaller, less than 1 that we haven't looked at. So we have 1 times 10 to the negative 3. If we write this in a calculator, it's going to come out like this. This is tens, hundreds, thousands. So let's see what we have here. If we go down to, we have milli, which is 10 to the negative 3. So when we plug that in, it is 10 times the negative 3 gram is equal to 1 milligram, or we can write it out like this as well. Now let's look at this next one. We have it written out different ways, so these are flipped. If you plug this into a calculator, it's going to come back with this in the hundredths place. So if we look at what this one is, it's centi, and that is in the hundredths place. So the prefix is centi, centimeter. 0.01 meter equals 1 centimeter. I know this is very confusing in the beginning. You trust me, this math doesn't ever leave you while you're in chemistry. You will have more than enough chances to start understanding this. You just got to make sure you put the effort in. Okay, and our last one. Which is larger, 1 milligram or 1 capital M, 1 megagram? And the base is gram. So remember, what's in front is the prefix. The base is the back part, so it's gram. So in this case, I spelled these out. I pulled them out. We have 1 milligram equals 1,000th of a gram. And 1 megagram equals 1 million grams. So obviously, it's going to be 1 megagram is much larger